Guys, welcome to my YouTube channel. Today we are going to see how to solve the differential equation 2xy cubed plus 2 plus 3x squared y squared plus 8 exponential to the 4y y prime equals to 0. So we are going to solve this differential equation using the principle of exact or inexactness. So the first thing we need to do is to express the differential equation in a form we can easily identify our parameters. That is in the form a xy dx plus b of xy dy equals to 0. So to do that, let us express our equation. We obtain 2xy cubed plus 2 plus 3x squared y squared plus 8 exponential to the 4y, all these times dy by dx equals to 0. Now that we have expressed our equation in that form, we need to multiply all through by dx. So we obtain 2xy cubed plus 2, all this dx, plus 3x squared y squared plus 8 exponential to the 4y dy equals to 0. Now that we have expressed our differential equation this into this form, we can see that a of xy is equals to 2x y cubed plus 2, and our b of xy is equals to 3x squared y squared plus 8 exponential to the 4y. Since we want to use the principle of exactness and inexactness to solve the differential equation, we need to show that the partial derivative of a of xy on dy is equal to the partial derivative of b of xy by dx. So we need to show that the partial derivative of a of xy with respect to y equals to the partial derivative of b of xy with respect to x. Knowing that a of xy and b of xy simply means that a and b are functions of both x and y, as we can see. So the partial derivative of a of xy with respect to y will be equals to, while differentiating, there is something that must be taken into consideration. When you're differentiating a of xy with respect to y, x behaves like a constant. So differentiating this, I obtain, since I'm differentiating 2x y cubed, then I'll bring down the power and subtract 1 from the power. So 2 times 3, I have 6x y squared. Derivative of 2, the derivative of constant is 0. Now differentiating my b of xy with respect to x. Same thing goes for the derivative of b of xy with respect to x. When differentiating my b of xy, I know that everywhere I see y behaves like a constant when I'm differentiating my b of xy with respect to x. So I'll obtain 6x y squared, bring down the power, subtract 1, and then y squared, the constant, then plus the derivative of all of this is a constant. Since y behaves like a constant, all of this is a constant, then the derivative of the constant is 0. So from here I can see that the partial derivative of a with respect to y equals to this, and that of b with respect to x equals to that. From here I can see that they are the same, so I can conclude, so the differential equation is exact. Now, since I've proven that the differential equation is exact, to solve it, I will let mu of xy to be equals to the integral Let my mu of xy to be equal to the integral of a of xy with respect to x plus a function f of y. Or I can still let my mu of xy to be equal to the integral of b of xy with respect to y plus a function f of x. Either of the options will still give me the correct answer. So let me take the first option and then proceed with it. So I'll let mu of xy to be equal to the integral of a of xy with respect to x plus f of y. This will be equal to the integral of a of xy. My a of xy is this, that is 2, the integral of 2x squared 2xy cubed plus 2, all this dx plus a function f of y. Okay, so from here I'm integrating with respect to x. So and while integrating, same thing goes when I'm differentiating. The y here behaves like a constant. So I have 2x squared all over 2 times y cubed plus 2x plus f of y. This function will be equal to a constant c1. Then I obtain x squared y cubed plus 2x plus fy f of y to be equal to a constant c1. So from here, this one will be the solution of my equation. So basically, the first thing you need to do is you let a function mu of x to be equal to the integral of this. When you integrate and you equate to a constant c1, this is basically your solution. But the next thing is that you need to look for the value of the function f of y, and to look for the value of that function f of y, you will need to differentiate. Now you will differentiate your mu of xy, that is this function, with respect to. So now to obtain the value of your function f of y, you will need to differentiate the whole equation, that is your mu of xy with respect to y, and equate it to b of xy. So what I'm going to do, I'm going to differentiate the function mu of xy with respect to y, and I'll equate it to b of xy. So let us do it. That is now the derivative of mu of xy with respect to y will be equal to the derivative of respect to y of x squared y to the power 3 plus 2x plus f of x to be equal to b of xy. So from here, the derivative of this with respect to y, this is a base like a constant, so I have 3x squared y squared plus 2, differentiate with respect to y. Now this derivative is a 0. Since the derivative of 2x with respect to y is 0, now plus, sorry, this is f of y. This is our f of y. Now plus the derivative of f of y with respect to y is f prime of y to be equal to my b of x. Initially, I obtained b of x to be equal to, this was my b of x, so to be equals to 3 x squared y squared 3x squared y squared plus 8 exponential to the 4y. So from here I can simplify. There is exponential to the 3, there's this and this that will cancel off. I send it the other side and then they subtract. I have f of f prime of y to be equals to 8 exponential to the 4y, knowing that this one will cross and then this will subtract the other one. So I have f prime of y to be equals to that, but I'm not looking for f prime of y, I'm looking for f of y. So I have f of y to be equals to the integral, let me say, just take the integral on both sides, the integral of 8 exponential to the 4y with respect to y. So I will obtain f of y to be equals to the integral of this, that is 8 all over f prime of y. F prime of this is 4 exponential to the power 4y. So I have f of y to be equals to 2 exponential to the power 4y, knowing that the integral of exponential to the power f of y with respect to y is simply equals to 1 all over f prime of y exponential to the power f of y. So basically we obtain our f of y to be equals to this. Now to obtain the general solution of the equation, we'll just come and substitute our value of f of y in this equation and then we get the general solution for the differential equation. This I omitted a constant here, plus a constant c2, the constant of integration, so plus a constant c2. So I have f of y to be equals to 2x exponential of this plus my constant c2. Substituting it back there, we obtain x squared y cubed plus 2x plus 2 exponential to the 4y plus c2 equals to c1. So basically I obtain x squared y cubed plus 2x plus 2 exponential to the 4y to be equals to a constant, let me say capital K in bracket, where K is equals to C1 minus C2. So this is the general solution for our differential equation. You are free to, so this is the general solution for our differential equation. So we can summarize all of this into few steps. The first thing, you verify if the differential equation is exact. Once you know if it's exact, you let your mu of xy to be equals to one of those two options and let them, then you solve the differential equation using the same method.